So the assumption that we're taking here is that PD is actually perpendicular to CE. If that's the case, then this is right angled here. And this is right angled. We can actually try to determine what the angle at the top here is going to be for us to break down this, for us to break down PD into pieces. So to break down PD into pieces, we need an angle. But what angle are we going to use? So we make the y-axis is the vertical. The x-axis is the horizontal, as always. Now, what we have to see here is this here is also, if I was to draw a horizontal here, if I was to draw a horizontal there, okay, not coming out too good. That'll have to do. If I was to draw a horizontal line, that doesn't look too horizontal. Not really happy with that. But if I was to draw a horizontal line here, what you have to see is that the angle that this makes here, theta, this angle will have to be the same as this angle here, theta. Do you guys see how? Do you see how those two angles are the same, or I have to show you? Let me show you. From inclined planes, you know to say if you have something like this, and you remember to say in inclined planes, you looked at the weight which always acted vertically downwards. The weight which always acted downwards. And then you changed the system so that the new y-axis was something like that. So this is what you did under inclined planes. And if the angle at the bottom here was theta, you know to say this would be the same as this one here. Is that okay?
Yes.
Yeah. And you still want to remember that this is the original y-axis, the vertical one. This is the original y-axis. But if this angle here is theta, then the angle here must also be theta. Right?
Yes.
Yeah. So by that logic, this is why I am saying that this angle here, if it is theta, then this angle here also must be theta. Another way that you can look at this is to say this angle is the same as this angle. Then if this angle, let's say, was 30, then this angle here has to be 60. And if this angle is 60, then this angle here has to be 30. So that you end up with this has to be the same as this. So this was just another way that you can approach the conclusion that the two angles are the same. Okay, so now that we know that this angle here is also theta, we no longer need this part. We can now use the theta here to break down PD into components. So if I wanted to find the vertical component of PD, remember PD is pointing downwards. It's going something like this. So if I wanted to find its components, it will have two. One component will be going vertically downwards like this, the vertical component, and the other component will be going like this, the horizontal component. So the horizontal component will be opposite to the theta, so it will be given by sine. So it will be PD. Then,
Sir,
yes,
to
please.
ask a question.
Go ahead.
Why are we not? Why are we calculating the angle for the for the perpendicular distance PD? Why didn't we just sum the forces in the x in the y to find the distance?
Okay, so if you look at PD, PD is not in the x. It's not in the y. PD has components in the x and in the y. So we can't, or you're saying summing the distances to get the angle? I don't know if the use of the distances there was...
To sum the forces.
Yeah, if you tried to sum the forces there,
The forces.
if you tried to sum the forces, would actually have a problem, because this will be in the y, this will be in the y, this will be in the y, this will also be in the y-axis, this will also be in the y, and our y here will also be in the y. But you see, PD will have two components. One component will be horizontal in the x, and the other component will be vertical in the y-axis. This is the reason why summing the forces just yet cannot work here. PD has to be in component form if we're going to sum forces. Have I answered that?
Yes, sir.
Okay. So, yeah, PD sine theta will be the x component, and the vertical part is side by side with the theta, so we're using cos. This will be PD cos theta. With this in mind, we can then come back to our diagram here. And instead of PD, I'll now replace PD with two components. One component will be a horizontal component like this. And we saw to say the horizontal component was given by PD. I keep writing F. This was given by PD. And then it was sine theta. And the vertical component was given by, I can write it here or I can write it up. Let me write it up. The vertical component was given by PD cos. So this is PD cos theta. Now I have all the forces expressed either horizontal or vertical. So it implies that I can now get the forces in the x and the forces in the y. Is that okay?
Let me just ask a question again.
Well,
how is it cos theta for the horizontal and the cos for the
okay, so this is what we have here. This is what we have. Let's make this bigger. And what you want to see here is, let's say sine works with opposite and the hypotenuse. Cos works with the adjacent and the hypotenuse. So all you want to do is you want to compare. If I am looking for the x-axis, x component here, how does it compare with the angle that I am given? You see that these two are opposite to each other. So if the side you're looking for is opposite, then it has to be sine. When it comes to the vertical part, you see that these two are side by side. Side by side means adjacent. If they are adjacent, you know you're using cos, so this part will be given by cos. This will have to be given by cos. So all I do is identify the ratio. After that, writing them is easy. That's okay?
Thank you.
No, cheers. Okay, so that part is done. We can now sum the forces. sum of forces in the x is equals to 0. When you look at this question, how many forces do you have in the x-axis? How many forces are there?
One.
No, it's not 1, 2. To the right as positive, we have Rx. To the left as negative, we have PD sine theta. Is it sine? Yes, sine theta. These are the only two, so this is equals to 0. From here, Rx will be equal to PD sine theta. We know what PD is. That is given in the question. Where is that? PD is 357.9. 357.9. Then this is sine 54.8. So what becomes the answer here? We get.
So why are we using that angle?
Okay, so just a minute. That becomes 0.5 kilonewtons. Why are we using this angle? Well, let's go back to the question. Firstly, this is the one given here, 54.8. Then next, we showed through a series of lines here that was the angle that related to what we are interested in, actually. Let me just go through that one more time. We had this as the section CD. And the angle given was this one. This was 54.8. So we pointed out to say that if we were to draw a vertical line here, and the force PD is acting along, this line. So what we saw is that from inclined planes forces, whatever this angle here becomes this angle, 54.9. And these two angles, we know to say these are alternating angles. These are supposed to be the same. This is 54.9. Then the one on top also has to be 54.9. So this is where PD was. So to break down PD into components, we then used, this is the X component, and it is opposite to the 54. So the 54, the X component becomes PD, then sine the angle we're comparing with, which is 54.9. So this is why we used 54.9. Is that okay? Not 0.9, 0.8.
Yes, it's okay.
Great. Okay. So yeah, this is how we get Rx. So we have found Rx, but it's not really what we're looking for. Kondwani, so far, are we doing the same thing?
Yes.
Nice. We now have to sum forces in the y-axis. To sum forces in the y-axis, let's look at what we have here. We have FCB going down, negative. The 150 going down, negative. And then we have these forces F at the one here and the one here also going down, so negative. but Ry positive going up. So I'll start with Ry there, positive, minus FCB, that was CB, yes. Next, I'll come to this component. This is the weight, remember, this is the weight. That's 150.78. So I'll say minus 150.78. Just keep in mind, let me make one mistake here and I will wait for you guys to correct me. So I've written that 150.78. Next, also going down, we have the 195.15. So we have 195.15. Then what else do we have? We have the applied forces. The first one perhaps is the components PD, PD and the component of PD that will go down, which is PD cos theta. Now, what is PD? So, okay, I won't make that mistake. I think you guys will be able to spot it since now this is when we're supposed to make the mistake there. The forces here are given in kilonewtons. So when using them, I have to keep in mind that the weights I am using are in newtons. So I either convert my weights to kilonewtons as well, or express these forces also to newtons. So what I'll decide to do, I feel it is easier to take everything in kilonewtons. I feel it is easier to use everything in kilonewtons because newtons will mean that those other values will just be a little bit too much. So I'll write these values in kilonewtons and everything else will follow in kilonewtons. So this will be FCB minus this in kilonewtons becomes 0.15078 minus this in kilonewtons 0.19515. Now I can bring those other values which are also in kilonewtons. Kondwani, are we still together?
Yes, we're together.
Kondwani, where did you go wrong then if we're still doing the same thing? Okay, so this is what we have here.
I think I got.
You what?
It's fine.
What were you saying? What did you say?
No, I think I got mixed up with the calculations.
Okay.
Yeah, I guess so.
Okay. Okay, so these are the values that we need, PG, PF, and PD. Let's use them. So the first one we encounter is I've left PD. PD will involve the use of the calculator. I have I have taken care of the weight. PF comes next, it's going down, then PG also goes down. Let me have those two. So those two are going down. PG goes down 128.9. PF also goes down 179.8. I have taken care of those except just that component of PD. The component of PD going down, you guys remember, PD in Y, we had PD cos theta. So let me just do PD cos theta. PD itself, 357.9. Then cos theta, that's cos 54.8. We have 206. So this is minus 206.3. I think this was the last one. Let's see. 1, 2, 3, 4, 5, 6, 7. So that is 1, 2, 3, 4, 5, 6, 7. Yes, we have accounted for all the forces there. Now we can add them up. So to add them up, I'll add the negatives. So that is plus, just the same one I had, 179.8 plus 128.9 plus 0.19515 plus 0.150, that's 150.78. Those are all the negatives. I get RY minus FCB to be equal to positive 515.35. You guys can verify this value. Okay. The next thing that we have to do here, we see that in terms of forces, we cannot really do anything here. So the next thing that we have to do is to turn to rotations and figure out what is happening in terms of rotations here. So we now want to evaluate the sum of the moments. Now, if we're going to evaluate the moments, the question is about what point? The best point to use here, just pick a point where you feel you know the least, where you feel you know the least. If at all, maybe you are clueless about this point here, then pick that point and let that be the point where the moments are being evaluated. But in this case, the best point to work with can be seen to be this point here. So let's evaluate the moments about that point. So what happens if moments are evaluated about that point?
I have a question.
Go ahead.
I have two actually. The first one being FCB. Where is FCB? I can't seem to find it in the question.
About E. FCB. FCB is not in the question. Have you got that?
Yes, I don't remember us finding FCB. As just explain again how you got FCB.
Do you see where it is? It's the force we are looking for. The force that is acting along the member CB.
Okay.
Yeah, that's the force that is acting along that. Yeah.
Yeah. The second question, how do we know that the force Rx will be applied to the right side and not to the left? And it's the same for RY.
You do not.
How are we sure that RY won't be done?
You do not know that.
That would be determined whether the answer will be negative or not.
Yes. You make assumptions. Remember, when dealing with free body diagrams, the minute they said it's a pin joint, then you know to say it will have two in the X and in the Y. I could have easily said one reaction would be like this, and the other reaction would be like that. Now, to know exactly the directions of these reactions, I'd have to solve the problem, find what these are. When I find Rx to be negative, it would mean that it is actually supposed to point in that direction. So I hope I've answered that.
Yes, thank you.
structures. Okay, now we want to evaluate the moments about this point E. Doing this implies that the forces at E do not cause rotation. So when I pick this point, the forces at E will not cause rotation. So the only forces that will cause rotation will be everything else except the ones at this point. So let's find the rotations due to each force. And all we have to do is identify whether it will be a clockwise rotation or an anti-clockwise rotation. Let me start with the weight, or rather, the weights. Let me start with this weight here. For this weight, we calculated it to be 195. That was 0.15. So that was the weight times the distance. What will be the distance? It's the perpendicular distance from where the pivot is to the line of action of the force. You see to say that is exactly this distance here. But what is this distance? We found it. It was half of 2.553. It was 2.553, but just half of it. That distance was 1.2765. So that is 1.2765. But will this be clockwise or anti-clockwise? If it is clockwise, negative. Anti-clockwise, positive. What do you guys think?
Clockwise.
Clockwise. So negative. We multiply. Yeah, so it has to be negative. We multiply this, the distance by 195.15. We get the moment here as minus 249.1 Newton meter. Again, just don't forget the other forces are given in kilonewtons. Once you decide to use this in newtons, there'll be conflict. You won't be able to add this, to add the moments properly because the units will be different. So the safest way is, even when getting these moments, convert these also to kilonewtons if you decide to use kilonewtons. So this could have been seen as 0.19515, so that when you get your moment here, the answer you end up with will just be the same thing here, but with the point here and the answer being in kilonewtons. I hope you've got that. Just multiply this, use the kilonewtons so that you don't stress when it comes to adding them at the very end. Moment 2. Let me get the moment due to this force here. And what was this force? This was the force at, that was at F. Is it at F? Yes, the force at F, PF. PF is 172. So we have 172.5 kilonewtons. So we need the distance here. So we're multiplying it with what? Let's write that down first. That is 172.5 in kilonewtons. We're multiplying this with what distance? So when you go back to the original diagram, do you see the distance we're using there? It's what? HEF. Yes, HEF. And don't forget, this is in millimeters. For the first one I did, I used the distance in meters. So even here, the units must be in meters. So in multiplying, this is 1420. So I need that 1420 in meters. So that's 1420, divide this by 1,000, that is 1.42 meters. Now I am guaranteed when I multiply, it will give me the same thing as this one here, so that I will easily be able to add them. So let's multiply by 1.42. We get 244.95, again, kilonewton meter.
So the 172, was it already in kilonewtons or newtons?
It was in kilonewtons already.
The value correctly.
It was in kilonewtons already. All these forces are in kilonewtons. Do you see that?
Yes.
Any questions before we go on?
Sir, I
Yeah.
have a question.
Go ahead.
Since the PF given in kilonewtons, why have you I don't know if you've divided it by 1000 and then multiplied it, and the units are kilonewtons per meter, kilonewtons meter.
I have not converted the PF. PD is 357.9 kilonewtons, and the PF is also 172.5 kilonewtons, and the PG is also 128.9 kilonewtons. These are given. I have not converted. Let's go to the other side so that you also see what I did. The only one that I converted were the weights. Remember the weights, I got them in newtons. You see the value. These are the values, PD, PF, and PG. See the one I used, 172.5, and 172.5 is in kilonewtons. You see that?
Yes, but for the first moment.
Yeah, so this is what I was saying. For the first moment, it was the weight. And the weight, I calculated it to be in newtons at first. So because this was in newtons, it was 195.15 newtons. I converted it to kilonewtons by dividing it by 1,000. Do you get it?
Thank you. I thought it was a force, and that was already given in kilonewtons.
No. The weight here was calculated. It's like this one here, I calculated it in newtons. Even this one here, when using it, I'll convert it to kilonewtons first. Okay, so one last thing here. Do you see that M2 as well will be clockwise? This will also be clockwise, implying that it will also be negative. Let's go to M3. I'll take M3 to be the moment due to this one. Again, this will also be clockwise, so it will also be negative. The force there is, that is PG, so that it's already in kilonewtons, so use it as is. But the distance, all the way from that pivot to the far end, we already calculated that distance. When we started, it was 2.553. Or if you want, you can still add the first one plus the second one there, so that you get the full distance there. So 2.553. So everything is set now. We have where? The distance is already converted.
2.553.
Uh-huh.
Okay.
Yeah, it's already converted. 0.553 by 128.9. So we get minus 329.0817. Again, kilonewton meter. Next, moment 4. We go back to our diagram. Everything in yellow has been sorted out. So the next one that we can go to is the weight here. Let's come to this weight here. Again, for the weight, we see that the mass is in newtons. We need it in kilonewtons. So in kilonewtons, we will divide this by 1,000. And of course, dividing it by 1,000, we'll just move the decimal point to, this will not be negative. The decimal point will now be here, 15078. Now it is in kilonewtons. So since now it is in kilonewtons, we are multiplying this by the distance. What will be the distance for this one? The distance will have to be from here to here. Do you know what this distance will be? What do we expect there?
Which distance?
For the weight here. The weight was located right on the center of this this section CE. So we now need the distance. I think you don't even need the actual diagram. You can use the actual diagram. Okay, even the actual diagram works. So what would be the distance? Let's say to be what? No, it's not DE. You have to see DE is for this force here, PD. The distance for this one has to be from here to there.
Half of 1.
Yes, half of 1.137. So we're going to multiply this with half of 1.137. So if we do that, that is 0.15078 by, yeah. It's what? Or where we got it from? Okay, so let me write this one down, then I'll show you where we got that one from. Okay. So where did we get that 1 point from? We got it from here. We added from C all the way up to there. So we added the 720 plus the 417, and we got 1,137. But we said that was in millimeters. So we divided it by 1,000 so that we get it in meters. That is how we got that 1.137 meters. But since this is the weight has to be halfway. So halving this gives us what halfway from here to somewhere there, what that one is. Have you got that?
So my question is that
It's I get you. It's the same thing. It's the same thing. Let me show you this. The distance from C to E, we actually got C to D, that length C to E, we got it as 1.972 meters. That was the length from C to D all the way, not C to D, C to E. So to find halfway of that, if I got halfway of 1.972, half of that will give me 0.986. If I was to get this now and try to find perpendicular to that force, because what I now have is this distance is 0.986. I want the horizontal one. so that it will be perpendicular to my weight here. The angle here is 54.8. You will see that this will still come out as the hypotenuse. They're side by side. So hypotenuse is 0.986. Then cos 54.8. If you did this times cos 54.8, you still get 0.56836 meters. You see that this is the same as half of 1.1, half of 1.137. Let's try that. That's 1.137 divided by 2. We still get 0.568. The only difference is it's coming out as 885. Here I have 836. Same thing. Have you seen that?
Yes, sir.
Okay. Okay, so this is a long class, but we're almost at the end. So for this moment, you have to see that it will be clockwise. So because it will be clockwise, this will actually be positive. No need to write that. The next one, M5. What will be our...
Can you...
Yeah?
Won't it be anti-clockwise?
Yeah, it will be anti-clockwise. That's why I wrote positive. I said one thing, I meant the other. It will be anti-clockwise. That's why I wrote positive. There was another reaction.
Which force are we?
Okay.
The weight. This one.
And then why are you saying it's going to be?
It will be rotating
Why are you
in
saying
this way.
it's anti-clockwise?
It will be causing rotation about the point E in that way. Rotation will be something like this. Do you see that?
Not really. So if I was like to use the same method you said of position a pen, the pen should it be like in a horizontal way or a vertical type of way?
It actually doesn't really matter. You can try to position your pen so that it lies along the length, along that distance. Then the force will be pressing the pen downwards. Do you see that the pen will swing anti-clockwise about this point because you're pinning it at this point? It will swing anti-clockwise about that point. Even if you decided to say that your pen will lie along that length, even if you did that, pin your pen here and then press it at the other end downwards. You should see that your pen will still swing anti-clockwise. Have we got that?
Yes.
Okay. Okay, so that sorts out the weight. We have 3 more forces to deal with. You can approach PD in component form, or you can approach PD as a vector the way it is. I will choose to approach it in component form. And if I approached it in component form, what will be the distance I will use for PD? PD in component form, we know to say the vertical component. I'm starting with the vertical component. So I am starting with this one here. PD in Y. For PD in Y, the moment there was given by PD, if you remember, it was cos theta. But what distance are we going to use for PD? What would be the distance to use there? PD in Y, the horizontal distance. Do you see that for PD, the distance?
0.7.
0.7.
Oh, sorry, 0.41.
Yes, 0.41. For PD, you see that the distance that will be perpendicular to the force will have to be HED, because the force is going to be a vertical force. This distance HDE becomes the one that we are using for this one. So that's 0.417. So it's 0 point because we've already converted it to meters. PD is 357.8. kilonewtons, cos 54.8 by 0.417. I always like putting brackets here so that you don't make a mistake of multiplying this with the argument of the cos. Let's see what we have there. That is 357.8. Then we have cos 54.8. We get 206, then by 0.417. We get 86. Will it be positive or negative?
Positive.
To be positive, it will also be causing anti-clockwise rotation. We can go to M6, which is the moment due to the x component of PD. The horizontal component of PD, we saw it was PD sine theta. But the question is, what will be the distance that we will need for this one? So let's go to the original diagram. What will be the distance for that force? No. For this one, we will need the distance from here. We will need the distance from here all the way to here. It will be the one that will be perpendicular to the horizontal force there. So you'd have to see that this is the horizontal force. I need to find this vertical distance here so that, but you have to remember that this is the triangle that you have. If this is 54.8, this will also have to be 54.8. So that we can now use the upper triangle here. The top part, this is the one that we found as 1.137. We can use this 1.137 to determine what this is going to be here, because this is right angled. So we'll use sine there. H will be equal to, not sine, tan. Sine works because we already know what the hypotenuse, we found what the hypotenuse is. But since I haven't brought it here, I'll use tan. Tan 54.8 is equals to opposite over adjacent, which is 1 point. Yep.
Like to use that method, since we're trying to find PD, the sine theta, right? We're trying to find that length. Rather than using the 1.137, why can't we just use the 0.417?
0.417. The one for this part?
Yeah, so that we can just get the height for PD, like from the point PD, because then.
Sorry. Yeah. I get you. Yeah, that's actually what we need to do there. The height that I'm looking at here is the full height up to there, but that's not where the force is. Yeah, thank you for that. I was making that error there. What we need is where the force is. And the force, it's not this distance that is actually supposed to be here. In fact, the force that we're going to use here, the distance I mean here, will have to be that 0.417. Because it's like the force is at this point. This is where the force is being exerted. So the force we are going for is in this direction. So we track it back. We need a distance that runs from here up to here. So we must use 0.417 and not that 1.137. So that is the one that we are going with there. Thank you for that, Zumila. I was making that error there. Okay, so from here, we can now use tan here, and we have tan 54.8 is equals to the opposite, which is what I want, over 0.417. And then H will be equals to 0.417, then tan 54.8. H will be equal to 0.417, then tan 54.8. So we get 0.5911. So we can then use that 5911, multiply this by what the PD is. So that's PD, and PD is 357.8. But now we need sine theta. So sine 54.8. That's 0.8. Yes. And we get 172.8 kilonewton meter. Okay, this is just M6. We now need M7. Any questions so far?
I'm still not so clear on how you got 0.591 as the distance for M6. I don't know
Okay,
if you can just rough sketch,
okay.
rough
So
explain me.
this is what we have. The force we are interested in is this one here. This is the line of action of the force. So we need the distance from here up to where the force is. But what we know is this horizontal distance from here up to here. This horizontal distance is the same as the distance from here up to there. This distance was given as 417 millimeters. In meters, that becomes 0.417. But then, in terms of the angles, if the angle here is 54.8, then the angle here also has to be 54.8. Of course, we see that is a Z. This has to be the same as that. So based on this, I then used tan to relate this angle to this side and to this side. Have you got that?
Isn't that for M5?
No, M5 is this one here, way at the far end.
Oh,
Yeah. So you've got it now? Yes, Kondwan.
oh, what if you were to get the force as just the force as a whole?
If you
So
are
meaning
to
you
get,
would get the distance,
you need the
the incline
distance.
distance.
Yeah, you need this.
Oh, okay.
Yeah, but to get that incline distance, you'd have to use the same triangle we made, where this is 0.417. But instead of looking for the vertical part, you'll be looking for the hypotenuse here. And since this is still 54.8, Now you just be looking for the hypotenuse. So you'd use cos here. So R, the hypotenuse, will be equals to 0.417 divided by cos 54.8. Have you got that?
Yes.
So this would have to be the force that you would use there. The distance, I mean.
So it's okay even if the distance isn't perpendicular to the force.
The distance has to be perpendicular to the force. In the case where you decide to use PD as it is, the perpendicular distance becomes this one. Observe that they are now perpendicular.
Okay.
Yeah. Okay, that's M6, M7. M7 is the final one, FCB there. And that is going vertically downwards. So since that is going vertically downwards, we know to say it will also have a clockwise, anti-clockwise, I mean. So it will be FCB, but then multiplying the distance. What distance are you going to use there?
One point 137.
1.137. So we have 1.137 FC